This first set of aromatic information is going to be presented just by me essentially narrating PowerPoint slides. It's not going to be very exciting. Not to say my other types of presentations aren't super exciting either. It's just probably the best way to kind of convey this information. So first of all, you probably have noticed that benzene is a pretty important moiety in organic chemistry. This is called the Kekule structure. There's actually a really interesting story about how Kekule came up with this on basically a hallucinogenic dream after using a whole bunch of drugs. I won't go into it right here because you probably don't care, but it is definitely an interesting story. So one of the things you'll notice about benzene, first of all, it's got this kind of like alternating system of conjugated double bonds. Of course, we talked about conjugated dienes. And really that's somehow special, right? The fact that all this conjugated system kind of happens in this cyclic structure. So what are some different interesting observations about benzene? By the way, all of these slides I'm going to post to the Canvas weekly module. If you want to look at the slides, there's a whole bunch more information here. I'm just kind of going through the highlights that allow us to talk about aromaticity. So what's special about benzene? Well, first of all, you'll notice that there's this 50-50 resonance hybrid kind of idea. Keep in mind that anytime we have resonance, that there's some sort of stabilization of the potential energy state of that particular thing. One thing that you'll often see, especially in Russian and German papers, is that they will actually just draw benzene like this kind of hexagon with a circle in it, which tells you that all of these bonds are actually equivalent until you notice there that the bond order of each one of these things due to resonance is 1.5. So it's not, when you look at this structure, it's not like this is a double bond, that's a single bond, that's a double bond, right? It turns out that they're all 1.5 bonds, right? And so that, if I drew that, I'm also drawing that, right? And so it's something that kind of helps us to think about the mechanism of some of these things in the future. If you contrast that with something like the butadiene, that conjugated system, where we talked about the fact that this wasn't just a pure single bond, right? It was a little bit like a double bond, but mostly still a single bond. That same thing is not true in aromatic chemistry. Each of these bonds is truly equivalent, not like what you might see in butadiene. So to really explain the stability of this uh, aromatic system here, we would have to go into molecular orbital theory, and we will at least briefly go into molecular orbital theory. But at least on a very basic level, you can kind of see this special situation that's set up by a benzene. Pretty much what you have is this like super planar six-membered ring that has this beautifully conjugated system of electrons both above and below the plane of the ring. It always reminded me a lot of like Homer Simpson, right? It's kind of like the double Homer Simpson. He loves donuts, so he'd really like benzene because there's really two donuts there. Um, so keep in mind, right, each one of these carbons is sp2 hybridized, and because of that, each one has a p orbital that's perpendicular to the ring that sets up this really beautiful system. Another thing which was noticed about benzene is it doesn't do the normal kinds of electrophilic additions that we're used to seeing, right? So in other words, like if we went through and took this thing, if this was truly a double bond and we treated it with bromine, you'd end up with this double bromine addition just like we've seen before. This, of course, you might imagine this kind of like being a 1,2 product, and maybe there'd be a 1,4 product. Who knows? But the fact is that you don't get that. What you get instead is what's called a substitution product. So this will lead us to talk about both electrophilic aromatic substitution and nucleophilic aromatic substitution, right? That's important to recognize that whatever these aromatic systems, for whatever reason, which we'll talk about, they tend to do substitutions as opposed to the additions that we've become kind of used to. I like this slide because it shows the stabilization of that conjugated system that we saw before, right? Which is really just, just a tiny, tiny bit compared to this huge amount of resonance energy, right? So it apparently is true that it's more than just the fact that we have this beautifully conjugated system. right? It must have some other special thing that's trying to be told to us. So let's talk about that. As I said, what's really going on in this aromatic stabilization has to do with looking at the molecular orbital picture of these pi orbitals, right? And we haven't talked a ton about molecular orbital theory, so I'll just kind of do a primer or kind of a quick review here. So keep in mind, right, this would be like this area right here is kind of how this thing would normally exist, right? If we just had all those p orbitals kind of coming together without any kind of bonding, we've got this potential energy axis right here, where up at the top that is high energy, and there's low energy down here. And so what we're looking at are just the pi molecular orbitals of the system. Keep in mind each orbital, just like atomic orbitals, can only fit 2 electrons, right? And so when you look back at that Kekulé structure and count up all those pi electrons, it turns out that you'd end up with 6. Right? And that becomes important because 6 pi electrons perfectly fill all of the bonding molecular orbitals here, right? Both this, kind of the double donut, and then also this other kind of bonding, the degenerate bonding molecular orbitals here. But the beauty is that these are able to accept 6 electrons. And up here, right, if we had any more than those 6, we'd have to start filling anti-bonding molecular orbitals, right? Or I guess we could also say that if we had any less than 6 electrons, we wouldn't fully fill all of the bonding molecular orbitals. So in that sense, what's really going on with aromaticity, and not just in benzene, but in every aromatic system, you have that perfect number of electrons to completely fill the bonding molecular orbitals of each of these molecules. Here's another way of kind of seeing the molecular orbitals of benzene. It's a little bit clearer here. So there you can see all of the electrons filling the bonding orbitals with none filling the anti-bonding. So it turns out that this kind of magic number of pi electrons will confer aromaticity on many, many things, and it leads to what's called the Huckel rule for determining aromaticity in something. So Huckel's rule, right? This is something that is going to be will allow us to actually predict aromaticity. And it turns out that it always is according to the 4n plus 2 equation, right? Where n is just any kind of integer. So this system, right, has 6 pi electrons. Well, that's if you plug in a 1 for the n, right? 4 times 1 is 4, plus 2 is 6, right? And so benzene definitely has that. You can also plug in a 0, right, and recognize that, oh wow, 2 pi electrons is enough to confer aromaticity on something. And of course, you can see that it kind of repeats, right? It's like 2, 6, 10, 14, 18, etc. And so there's a couple of other requirements for things to truly be aromatic, but Huckel's rule is probably the most important one. And probably the best way to talk about what is required for aromaticity is to see actual examples of things that are aromatic and things that are non-aromatic. It turns out there's something called anti-aromaticity. That is, if you can imagine aromaticity as something that gives unusual stability to something, anti-aromaticity does the exact opposite. And it turns out we can also determine if something is going to try to avoid anti-aromaticity by doing all kinds of weird bends and turns and everything else. It really just, most systems are going to really try to avoid that 4n pi electron number. So other things that are required that I'm not sure are in slides, but I'll mention it, right? Huckel's rule is not, it is necessary but not sufficient for ensuring aromaticity. The other things that you need are, if you think about benzene as the model, right, you need unoccupied p orbitals, right? So in other words, you need, or I shouldn't say unoccupied, but unhybridized p orbitals, right? It has to be in a ring, and all of those p orbitals kind of have to have a neighbor, right? And so really, in terms of whether something is aromatic or not, right, we first check for Huckel's rule, then we checked that things are cyclic, and then we check to make sure that every single atom of the ring has some sort of p orbital. So there's what I just said, stated a little more concisely. It's probably helpful to see a couple of examples here. So something like this, right? If we were to count up all those 8 pi electrons, we'd recognize that that should be anti-aromatic, right? Well, it turns out in order to avoid being anti-aromatic is it will actually bend bonds that aren't normally bent, right? And so this molecule actually will kind of readjust its molecular geometry to avoid anti-aromaticity. And what we're going to see is the opposite of that, right? The idea that going towards aromaticity, a lot of times we'll see that as kind of a driving force in the way that these orbitals will hybridize, right? We'll actually hybridize unexpectedly in order to get towards aromaticity. And so we'll see a couple of examples of that. So let's see. Here's just a picture of a couple of other, either non-aromatic or aromatic systems here. As I said, benzene's not the only aromatic thing. It also turns out that aromaticity plays a role in certain mechanisms. And so here we can see what's called the cyclopentadienyl anion, right? It's this negatively charged thing that also has that perfect Huckel rule. And the reason why this is important is if you imagine these acid-base reactions as kind of a, as kind of a yin and yang situation, if you have some sort of hydrogen that's kind of preventing this thing from being aromatic, right, because there's that sp3 hybridized thing, well, it might make sense that this molecule really, really, really wants to get to something that's aromatic, right? And so what it turns out that this kind of idea of aromaticity in a reaction can actually be pretty important because like it'll tend to make things more or less acidic, right? Here's a perfect example of where this thing really should not be acidic, but aromaticity is a spectacular driving force, right? And so here's a perfect example of something that's unusually stable, right? This cyclopentadienyl anion, right? It's got all kinds of resonance forms, and it's aromatic. And then you look at this other thing, and you look at this and you think, oh man, well, look at all the resonance forms here. Well, it turns out if you were able to, even though you could draw all these resonance forms, you actually have an anti-aromatic system. So this is not an example of where resonance is appropriately applied in a sense, right? And so if you were to actually look at the picture of this thing, much like that Cyclooctatetraene, I think it was, is that this cyclopentadienyl cation, in order to avoid anti-aromaticity, will do all kinds of bizarre kind of bends in the bonds to keep it from being planar. That's not to say that cations can never be aromatic, right? Here's a perfect example of something I don't know. You don't have to know that name. I certainly don't. But what's important is that you could look at this structure and say, hey, man, that thing is definitely aromatic, right? We've got our 6 pi electrons, so we're following Huckel's rule. That positive charge is going to make there be a p orbital that's unhybridized on there and perfectly planar, right? And so here's a great example of something that is in fact a cation, but is aromatic. It turns out that we can also have what's called heteroaromatic systems. Pyridine's a great example of that, right? And so this guy right here, right, he is going to be overall an aromatic thing, right? 1, 2, 3, 4, 5, 6 electrons. In your homeworks, eventually you're going to start to kind of recognize that we can only count electrons once, right? And so in other words, like we are not able to count those electrons towards the Huckel rule because those guys are actually involved in this sp2 hybrid here. We're only going to count the electrons that are part of the pi system. So there's just kind of an example of something that's a prototypical aromatic thing that contains something other than carbon. There's a whole bunch of them. Here's something else that's aromatic, right? We've got 1, 2, 3, 4, 5, 6 electrons. This thing is called pyrrole. And so one of the things that we'll eventually talk about, right, in terms of that lone pair of electrons and this thing acting as a base, most of the time, amines are really good bases, right? Well, it turns out that those 2 electrons being involved in the aromatic system means that this thing is going to be a not very good base. right? Because the second you protonate that thing, you turn it into an sp3 hybridized center, which of course destroys aromaticity. So you'll see that the equilibrium is unexpectedly way towards starting materials here. When you look at these things, which many of which are involved in like DNA and such, or nucleic acids in general, right? You actually see aromaticity having a pretty interesting role here, right? So like these electrons are not involved in the aromatic system, so they tend to be very basic. Something like imidazole, which is a part of a pretty important amino acid called histidine, you'll notice that there are some nitrogens that are very basic, and then you've got other ones where those two electrons are involved in maintaining aromaticity, so they're not very basic. Same kind of thing can happen in the purines. So we've talked about a couple of these. Here are a couple of other aromatic moieties there that contain or heteroaromatic moieties that contain things other than carbon. You can also have these crazy big systems of multiple aromatic moieties or multiple benzenes kind of fused together. Interestingly, like a lot of these things are both what makes like charcoal grilling so much tastier than propane grilling. It turns out that these things, for whatever reason, are typically a part of char and a little bit tastier to us. Unfortunately, they can actually intercalate into DNA, so if you eat a ton of that stuff, it's not the best thing in the universe, so everything in moderation. This naphthalene always has like a special kind of place in my heart because it always reminds me of my grandmother, right? She used to have a whole bunch of mothballs in the closet, and so she'd often smell like mothballs, and that's naphthalene is the main ingredient in mothballs. And so these are all examples of those fused ring systems. So if you're interested to look at a couple of other kind of aromatic like theory kind of involved slides, take a look at this, read your book. If you have any questions, ask me in office hours. Oops, one last thing. I always forget to mention this slide or to mention this to people. There are many special names for aromatics that you really are just going to have to memorize. We'll talk a whole bunch about each one of these, but all of these ones are probably things that I would throw in a note card just because it can really make your life a little bit easier. I would say probably these four, and then these two are the most important ones to know. Okay, now I really am done.